Yeah, this is going to be a bit of a meandering talk. I'll introduce some concepts around sort of how we deal with big data, how people access it, how you can make that access more optimal, and some of the problems we face. And then we can sort of go in and explore the ecosystem and look at whatever topics are most interesting to you guys. So, there we go. Right. So I call this talk going big with, sorry, give me 1 second and adjust this mic. I call this talk going big with I/O because a lot of our problems these days stem from the fact that the data that we're working on does not fit on this. It will not fit on your laptop. You can't download it in a reasonable amount of time. And sometimes if it's, on the scale of a petabyte, this data is so large that even processing a small chunk of it is beyond the capabilities of your laptop. So, you might say, all right, this is kind of a solved problem. You spin up a cluster, you launch, 100 workers, and you process your data. That's expensive. And it's also painful, right? You have to sign up for this account, do all of this stuff, blah, blah, blah. So a lot of what I'm going to talk about today is sort of how you can use big data to solve small problems. And also big problems, but a lot of my work has focused on small problems. So first, let's talk about this sort of new age data access. Earth observation and climate data is often in the petabytes. The data collected even from a single satellite will no longer fit on a laptop. This is not a new problem. Solutions have been tried before. You break up your data set into multiple files, you tile it up, you create these spatial chunks, maybe you store it on the cloud, or maybe you allow the user access through some special purpose server, like a web content system, which is an OGC format, or something like that. But all of these solutions come with problems. Multi-file data sets mean that the user has to know something about the structure of the data set. If you have, I'll give you an example, Copernicus DEM, right, which probably most people here have used. They tile it into 1 by 1 degree tiles. Each tile is a single file. You have to know the format of, if I want the data around this area, okay, I have to find which tiles it intersects. I have to know, given a tile, what's the file name of that tile? How do I get to it? I have to download this thing. It's not easy, right? Large file storage on the cloud, if you have one single large file, even with HTTP range requests, it's hard to download, it takes time. Your queue might get backed up as there's a lot of people doing it. Breaking up large files is expensive because cloud storage providers charge by the number of objects. So S3, right, which is probably the leading cloud storage service today, every file you put on it is called an object. It's a thing. And the more things that you have, the more that they'll charge you. Of course, if you want your user to be able to get only the data they need, you have to have a lot of things because your data has to be chunked up in relatively small chunks. So this is a problem. Special purpose servers need maintenance and they need support from libraries on the user's end, right? For example, in Julia, we don't have support for all these OGC standards of web feature service and whatnot, except through GDAL, which is again slow. It's not guaranteed. So to paraphrase a much more meaningful saying, I have a dream. And the dream is that a data set should only be represented by a URL. It doesn't matter the size, it doesn't matter the content. That's all that you really need to know. You just have one URL, you access it, and then everything else is readable from the metadata. Users should be able to care about this, but they shouldn't have to care about this. And I'm not necessarily talking about how you use the data, right? Once you get the data that you need, how you use it is up to you. But the problem is, in fact, getting it to you. So how do we get there? How do we get to this dream? So on the right-hand side, I've got some little demos. You can use zar.jl, and you can open an S3, some zar file on an S3 bucket. You can use rasters and zar datasets, and you can open some zar file on an S3 bucket. I recently wrote a Julia package that reads chunk manifest, which I'll talk about in a bit. So you can do that. There's a Julia package called file paths base, which lets you actually, in conjunction with the S3 library, it'll let you treat paths on AWS S3 as paths on your local computer. So you can read directories and download files very easily. But how do we get there, right? How do we get to this dream? So multi-file datasets can be unified using these. Oh, go ahead.
This is a very stupid question, but
Mm.
I've never heard of S3.
Oh, it's basically what they call object storage. So fundamentally, it's just a web server, right? What it's doing is you can request a key from it, and a key is some string, and it will give, if that key exists in its storage, it will give you back some vector of bytes, which is just the file, and generally the keys are formatted in the same way as directory paths are formatted on our computers. So
It's cloud storage.
cloud storage.
Oh,
Yeah.
okay, it's all web stuff.
It's basically the monopolies and it's still
Okay.
for objects and we can access right into our.
Yeah, it's essentially cloud storage, if that makes more sense, yeah. So modern data storage methods like, I'll talk about this sharding, where you concatenate multiple chunks into a single file, make S3 hosting a lot less expensive. As Martin spoke about quite a bit, if you optimize your data for the cloud, you conceptually separate the metadata from the data, right? So the metadata is readable without trawling through the entire file. Simple HTTP and S3 interfaces in most languages mean that we can extend this idea of the local file system to the web. So you just treat I mean, I'm sure most people in this room have had very, very bad experiences with FTP servers, right? Oh, I connected, but the connection broke, and this and that and the other, and I had to re-authenticate, right? So HTTP and S3 are more transactional. You don't have to keep an ongoing connection. You don't need a session. You don't need any of that. And the last thing, and probably the most important thing from the user perspective, is that all of these operations need to be asynchronous. What does this mean? Well, when you download something, it takes time to download, right? And so if you're doing this serially, you download one bit of data, you download one bunch of data, you operate on that, then you download the next, you operate on that, then you download the next, you operate on that. The vast, vast, vast majority of your time will go in downloading, and your computer's sitting idle. So instead of that, what you can do is you can request 50 pieces of data at once. They all keep downloading, streaming to your laptop. The moment one finishes downloading, you process that and you move on. And you keep essentially receiving this data in a queue and then processing it as it goes along. So, and that'll become a bit clearer, I think, when I show this demo. But the next question is optimizing access. So I can have a very large data set. Obviously, I don't want to download the entire thing, right? So at the end of the day, all data is just a vector of bytes. That's all it is. That's how it's represented on your hard drive, on your file system, whatnot. Storing a single 1 terabyte byte vector is generally understood to be a bad idea. So let's not do that. What we can do is we can break it up into these so-called chunks, which are basically rectangles or rectangles in n dimensions, hyperrectangles, and the shape of the chunk dictates the optimal form of access. So and fundamentally, the idea behind chunking is that you download only the data you need. But what does that actually mean? So let's take a look at this data. Let's say this is some example data set. I just put a picture of the Earth, but it could be anything. Now, if this data set, if this is just one file, if this is just one massive chunk, if I only care about something in Iceland, I have to download the entire thing to then decompress it and look at, and then I get the data. I can subset the data around Iceland. Now, let's say I chunk that into chunks that are, I've essentially done, if this one was 5400 in X, 5400 pixels in X and 2700 pixels in Y, then I've made chunks which are 1800 pixels in, 1080 pixels in X and 540 pixels in Y. So essentially there's 5 chunks per axis, right? And so you can see this is a grid of 5 by 5. Now, if I want something from Iceland, all I have to do is I have to download this small chunk and then subset that. So the amount of data that I'm downloading is substantially lower. Now, this is one chunking pattern, but I can do anything. I can do this, right? If I want to scan across the globe, if I just want, so a lot of rasterization algorithms, for example, polygon rasterization algorithms, they operate on a scanline basis. So you actually do one line across the entire plane, and then in that line you can tell which pixels are within and out inside the polygon and which pixels are not. So in that case, this is a very optimal chunk pattern because I download this and I run all of my complicated algorithms on this thing. Then I download the next one. I run all of my complicated algorithms on that. So all of the data that I require is made available to me. So, but, right, if I wanted to access just a small chunk around Iceland, then I have to download this entire thing to get to this. So the choice of how you chunk things really, really affects how your user will be able to use your data, how long it will take them. And chunking is, of course, not restricted to 2 dimensions. It's also very interesting for n-dimensional data sets. Let's talk about 3D for a second. Let's say I have a 3-dimensional data set, 2 dimensions x and y, 1 dimension time. Right? It's some time series of, let's say, Earth observations, weather measurements, simulations, whatnot. If the users of your data set are interested in looking at one small region of space, but across all time steps, then you want your chunks to be very, very long in time and very, very small in space. If they're interested in global overviews, right? You want to look at the average temperature of the world or something like that, but at a single time step, then you want to have chunks which are very large spatially, but small in time. So I'll show you, this is a visual example, right? So this z-axis, the upward pointing axis, is time. The x and y axes are x and y. And you can see that these chunks are very, very long in time and very small in x and y. So if I just want data from this chunk across all time, it's very easy. But if I want to get a global overview for one time step, it means I have to download the entire data set. Right? So you can see where these trade-offs sort of start coming into play. Mm-hmm.
And so what is stopping people from making too many chunks?
What is cost? Cost and the fact that, okay, when you download something, right, there's sort of 3 stages to it. One is you send the request, the server processes the request, and then you download the data. So with small chunks, the time taken to download the data will be small, but the time taken to send the request to the server and for the server to process that is a fixed cost, right? That's static. So if you have too many chunks, then the overhead from requesting your data from the server is very high. But if you have too few chunks, then of course you're downloading too much data. So there is a trade-off there that you have to manage based on what you believe your user will do. Go ahead.
So, just to clarify, so we're not actually storing the chunks ahead of time. We're storing the entire image and then we're chunking it somewhere in the back and then we're pulling.
No. The chunks are stored separately.
Understood.
So actually, you know what? Let me see if I can do this.
Anshul, it might also be helpful to mention that a chunk is the compressed unit.
Yes. So the big thing about a chunk is that this thing is a single unit. So if I want to compress that, I just compress this individually, then the next one individually, then the next one individually, and so on and so forth. Right? So what you don't have to worry about in this case is you can decompress them also individually. Because if you compress the entire thing, then you have to download the entire thing to decompress. So go ahead.
How to figure out the best number of chunks like that?
Yeah, so well, let me show you the next slide. And so this is an example of chunks which are very wide in space but very small in time, right? So if I wanted a global overview at some time step, then I would just get 4 chunks instead of all of the chunks of the data set. So the question that you have to answer is, what are your users trying to do? So, and it may very well be that you want to do both, right? So you just put up 2 copies of the data set. One is chunked in space and one is chunked in time. That's also something you can do. Does that answer your question or not really?
Yeah.
Cool.
My question is, with chunking, is the quantity of the data affected at all?
No, not at all.
You're just cutting it and you're not having an impact on
No. You're essentially chopping the data up into a little bit, but there's no loss. The only loss that you could have is if you choose a lossy compression method. So, for example, a PNG is completely lossless, right, in images. But JPEGs, you'll notice that they're smaller, but the quality is a bit lower and stuff like that. So if you choose the wrong compression method, then yes, absolutely. But in general, with the defaults, there will be no loss. So yeah, so as I said, these are just 2 different examples of chunking schemes. right? And so you of course have to choose the one that works for you, that works for your users. But if I look at this again, this is a 10 by 10 grid. This is about 100 chunks total, right? And this is, let's see, it's 10 by 4, so it's about 40 chunks. So the more granular the chunks, the more of them you have. And as I said, that means that on S3 you have a lot of objects, you have a lot of cost. Now, in order to avoid this, very recently in the ecosystem, this idea of sharding has come up, where you concatenate multiple chunks into the same file. So if you are storing one chunk as one file, then you run into these S3 issues, where just because of cost, you have these gigantic numbers of chunks. But if you concatenate chunks into the same file, what you can do is you can essentially, with the HTTP range requests, you can decrease that cost substantially. But the cost that the other complication that you introduce is that, of course, now you have this file with a bunch of chunks, and you have to store the offsets for each of those in bytes and so on. Excuse me. So it introduces a lot of complication, but it can also improve your web caching speed if this is a data set that you're delivering to a lot of people. It can improve download speed if you use it correctly, things like that. So, sorry, someone had a question? No?
I was just going to sharding is what we saw in the previous presentation, right?
Yes. So what Martin was talking about was mostly single file data sets, right? So a single file is, in that context, is a shard. And then if you have, I mean, at NASA and places like that, you have these data sets with millions of files, right? And so each file is a shard. Inside that, they have chunks, which are compression units. So let me give you a more visual example, right? This is the same chunk data set from before, but I've put these little white lines. And so now imagine that each of the large boxes is a single shard, right? That's a single file, within which you have these smaller compression unit chunks. So what you can do here is, of course, each of these small chunks is individually downloadable, right? But this is one object, this is one object, this is one object, this is one object. So now, if each shard has 25 chunks and there's 25 shards, you have decreased your storage costs by a factor of 25, because you've decreased, at least in the dimension of number of objects. You've decreased the number of objects that you're storing by a factor of 25. Alex, go ahead.
The price per object is a component of the cost.
Right, it's not the whole cost. Yeah.
Saving your storage.
Yeah.
That the storage costs are still the dominant cost.
Yes, they're still quite high, but and it's not just that, right? You can also, if you want to use an older workflow, you can also download the entire shard. If you know that you require the entire shard, you can just download that and then decompress on the fly as well, right? So
is each one of these considered a shard, or each of the, I want to say square, but it's all squares. I mean
the bigger ones and the smaller ones. The bigger ones are shards.
Right. And then the individual
Yeah.
squares. Those are the chunks.
Those are the chunks. Yeah. So I'll show you this graphic, which should probably, I probably should have shown this earlier. But in the context of your data set, right? This is just one array in the data set. You have a shard which holds a bunch of chunks. And so the shard is the unit of storage, and the chunk is the unit of compression or transformation or what have you. So in this case, in a lot of situations today, if one shard is one chunk, then this and this are just the same thing. But in the general case of, like, I send you an etcdf file, or I send you an HDF5 or a geotiff or whatever, then that file is a single shard, and then that contains these multiple compression units. So this all sounds a bit familiar if you work in geospatial, right? I'm talking about these shards and chunks and whatnot, but really this is just the same multi-file dataset model, right? You have one file per some, let's say maybe 1 by 1 degree, maybe something else. You have one file per 1 by 1 degree square. And then inside that file, you have chunks based on whatever your requirements were, right? But the beauty here is that it's concatenated into a single logical data set. So I only have to load one thing. right? From my mind, the only code I'm writing is one line, as opposed to this. If you have actually multiple independent files, then you have to load each file, or if you're using X-ray, you load the multi-file data set, which takes time and stuff like that. So the user doesn't have to know about it. That's the cool part. So yeah, if each shard is an HDF5 file, or if each one by one tile is an HDF5 or a netcdf, then each chunk is the chunks of the file. So now I've been talking about this ZAR thing, but what actually is it? So ZAR is an open format for storing large multidimensional data. It's flexible, extensible, multi-file by default. So the chunks are stored in this like hierarchical directory structure, but the metadata is stored in separate files. It's stored as JSON. So it's human readable, it's not very large, and the nice thing about ZAR is because it's community extendable, chunks can be compressed and transformed in a lot of ways. So it was very difficult, for example, to store variable length strings in binary files. Not all file formats had support for that, but in ZAR, it's easy enough for you as a user to just add that. Or if you have some new compression algorithm that you believe is good for your particular use case, and I think Milan wrote one of those actually, so we have someone here who's done that. This is the bit information thing that they added to numcodecs. But yeah, you can just create a new codec as and when you like. And of course, that doesn't mean that everyone can use it. You have to get it supported by the community. But it's a lot more accessible than it used to be. Where earlier in HDF5, you would have to go through this like arcane approval process and write C code and all of this stuff. So let me just show you quickly the directory structure of ZAR. Can everyone read this? I tried to zoom in as much as I could, but so this is my top level directory. It's called test.zar. Inside here, I have a file called .zgroup, and I have a bunch of folders, but each folder is equivalent to either a group or an actual array. And so a group is just a collection of variables, right? Go ahead.
So test.zar is just one ZAR file.
It's a folder.
It's a folder.
It's a folder that you call test.zar.
So these are file system that you're
Yes. No, it's not the actual file. This is a file system, right? So that is one potential drawback of ZAR, right? Is that it has to in size, it's not necessarily larger than HDF5 or what have you in physical, like actual size on disk, but the structure is a bit complicated. So you can zip this up and it'll work. Most ZAR readers can read a ZAR within a zip, but it's just one more thing you have to keep in mind. So ZAR was really meant for cloud storage and that kind of thing. Because if you think about the directory path it takes you to get to this, right? test.zar/ti/0. So the ability to figure out the file that you need is actually very simple. So there's this thing called time, this thing called x, this thing called y, and my actual data set, which I think I left unnamed for some reason. But so you can see that here, for example, these are all vectors, and so these all just have one chunk, and then this unnamed is a three-dimensional array. So its chunk is 0.0.0 because it's chunk 0 in dimension 1, 0 in dimension 2, 0 in dimension 3. So this is kind of chunk indexing. ZAR is not natively dimension aware. So ZAR will not know that this unnamed array connects to this time or this x or this y vector. But X-array and most ZAR readers these days, they've introduced this key called array dimensions, which I'll show you in a bit, which basically, it's a metadata key which tells you what this is. Very similar to what happens in climate and forecast compatible files like netcdf or things like that. So let's look at, I'm going to look at this file now, x, the .zarray file in x. So it tells me that the chunks are of size 100 and there's one dimension. Then it tells me there's no compressor, so I haven't used any compression. This is a Python terminology called dtype, which basically just means data type, right? It is an 8-bit integer, so int64. There's no filling value. There's no filters, which are just arbitrary data transformations. So you can do, for example, scale and offset through a filter. And it gives you the order, which is column first. it gives you the total shape of the data. So in this case, it's 100, so there's only one chunk. If it were, for example, 101, 102, then there would be, or up to 200, there would be two chunks, right? And then 300, so three chunks, and so on and so forth. And the ZAR version, which is 2. So now ZAR version 3 is kind of out. It's not really widely supported beyond Python. Python is itself pretty big, so it's kind of out. And ZAR version 3 introduces a couple of new concepts, but fundamentally, it's still the same thing. So that was the ZAR specific metadata. Now we get into this file called, and this is all JSON, right? So this is all JavaScript object notation, super easy to parse, super easy to look at. Now this is Z attributes, which is completely user-defined attributes. And so in here, you'll see that there's this key called array dimensions, which is X, right? And there's this key called axis, which is capital X. So that just means that this is the X-axis of the data. This is more of a climate forecast convention thing. And so if I looked at that unnamed thing down here, right, and I looked at that zaddrs file, this array dimensions would have been X, comma, Y, comma, time. So if that sort of helps make more sense. Yeah, again, just to reiterate, the way a chunk works in ZAR is that this is your entire array. Within that, you have these, let's say you have 4 chunks in that array. So these are addressed by A.B.C, depending on the number of indices, number of dimensions. Now, what happens when you read a chunk is that you'll recall that there were specifications for a compressor and some filters here. And so actually this is what's happening when you write a chunk. So this is raw data, let's say, right? This is your numbers, maybe if it's temperature, it's in the range from 260 to 300 or something, right? These go through filters, so that might be, for example, the scale and offset filter. It might be some form of quantization, some form of delta encoding, stuff like that. So delta encoding is where each value is relative to the one before it, right? So there's a lot of different things you can do here. And then it goes into a compressor, so that can be zip, BLASK, LZMA, lurk, all that stuff. Once it's gone into a compressor, you essentially just have a vector of bytes, and that vector of bytes gets stored as a file. So this is essentially the structure of ZAR, if that makes sense. And it's very similar to what you have in HDF5, right? It's very similar to previous solutions, but it's just a bit more understandable and easier to write. So for example, there's a reader for ZAR in JavaScript, right? Which Alex uses on a web page. Now, if you try to tell me that you could upload HDF5 to a web page and have that read automatically, I would be very impressed. Without a server, mind you. No server, no backend, no nothing. This is all running in your browser. So the core ZAR spec is super simple, right? It's just, given some indices of an array, can you convert that to which chunks you need? Given a chunk, can you convert that to data, or can you go the other way around? Given the data, can you compress that into a chunk? And the last question is, of course, given a chunk index, how do I get that chunk physically? And so that could be either, simple file system, could be S3, HTTP, Google Cloud. You could go into a zip file and decompress on the fly and look at that. So that's ZAR. And now, oh no, I seem to have misplaced this. Oh well, I'll find it. So let's talk about Kerchunk. So this is a name that you've probably heard floating around a lot. But what is this thing? Well, we love the ZAR interface. It's really simple, straightforward, can do a lot. But we need to access data that is not stored in ZAR. We need to access all of this data since 1970, right? Which is when satellite imaging started to take off. And that's all stored in, if you're lucky, NetCDF4 or HDF5 or GeoTIFF. If you're not lucky, then it's stored in something else. GRIB, FITS, which is astrophysical images, all these even more obscure file formats. How can we do this for multiple files, for all of these crazy data sets, without stepping out of the ZAR world? And so the fundamental concept is that a chunk is a chunk, it doesn't matter where you go, right? Any data format that stores chunks must by definition store them in as, some vector of bytes. And if you give me a vector of bytes and I know what you've done to it, I can probably undo that. So we know that HTTP requests allow you to get specific byte ranges from files. So the concept behind kerchunk is that you create what's called a chunk manifest that maps logical chunks to physical byte ranges in some random file, arbitrary file. Right? And so this maps chunks, this maps the chunk address 0.1.2 to some range of bytes inside some HDF5 file or some grib file or something. So, you go from a chunk address to a file, let's say myfile.nc, and some range of bytes. Maybe you go from byte 1204 to byte 5502. I just made these up, right? This mapping is stored in a JSON file. It's created by going through a data set, and this can be one file, multiple files, anything really. And you open each file in the data set once. You retrieve all the metadata, you compute the position of each chunk in the larger data set, right, in the global data set. And then, once you pass out all this metadata, you store this information in the kerchunk JSON file. And this allows, theoretically, millions of files to be referenced and accessed from this one single data set. So, I duplicated that. So this is an example of a kerchunk mapping file, right? So what they've done is each key, this is JSON again, each key, it's kind of like a dictionary, each key here is the name of the file or the path to the file. And the contents can either be a string, which is just the contents of the file, or like this, it can be a path to a file and some byte offset and some byte length.
Is this still within the ZAR spec or is it an extension?
This is an extension to that. So it's, well, what has basically been done by kerchunk is that they fake your file system. So what you show ZAR is a file system that has all of these keys, right? But when ZAR tries to read this file, kerchunk, or in this case Python's fspec library, which is a part of, it's not part of kerchunk, but kerchunk functionality is implemented by fspec, right? So fspec meaning file system specification. So Python's fspec library will go retrieve this byte range from this file and present it to ZAR. So that means that this can be anything. This doesn't just have to be from one file. This can be from file 2.nc, file 3.nc, right? Or tile underscore E60 underscore N25, right? It could be anything.
Can I ask another question?
Mm-hmm.
I don't see in this list the indication of what do you use to read the file or that software. Is that sort of assumed, like this is an access list, right? So you know sort of here what you use to do the other. You know what I mean?
Yeah, so in terms of software, so this whole ecosystem started out in Python. So in Python, if you pass Xarray a reference to this JSON file, it will understand that. And then, but there's no, okay. So do you mean specifically once you've got the chunk, how do you decompress it? Or how do you interpret that? Or like,
Let's say that these are flat binary or grid or next year or
Mhm.
CSV or whatever, right? But you need to know how to get to the vector data you need to expose it from the store.
okay. So you're asking how you create this file,
No,
essentially, no.
I think you are starting to answer it with Xarray. So
Okay.
Xarray has-
Sure. Yes, okay. So you tell Xarray that this is a grib file and that's how you open it. So for this, how do you tell it that this is a kerchunk file and that's how you open it?
Yeah, so
Yeah. Yeah.
Fast.
So that's what I just did actually a couple of months ago. So Alex and I, we wrote a kerchunk interpreter for Julia. So it basically does the same thing, a similar thing to what I described in Python's fspec, is that Julia has a zar.jl, right? And within zar.jl, what we do is, or rather, as an extension as a package that depends on zar.jl and extends it. What we do is we define a specific zar storage mechanism, which is backed by this JSON file. And so for example, so this zar storage mechanism backed by this JSON file. Then what happens when zar.jl requests a file from our store, from our storage mechanism, Kerchunk.jl looks up where that key is in this list. It finds it. If it's a string, then it just returns the string. If it's a reference, then it downloads the relevant bytes and returns those. So the way that you would actually use this is you would load Kerchunk.jl and zar.jl. And if I go all the way back here, I can write it out later, but essentially using Kerchunk, using zar, if you're using the rasters, maybe you use zar datasets if you have a CF, if you know it's CF compliant, which most Kerchunk datasets are, because they come from CF compliant files in the first place. And then you essentially just start with reference : / wherever your Kerchunk file lives. And that essentially sorts it out. So does that make sense?
Yeah, no, I think so.
Cool. Okay. Yeah, if it helps, I can just walk through the tests of Kerchunk, and there's a little demo there, which might make it a bit more obvious.
So in that, you can't see actually on your screen there that you're actually forcing rasters to use zar source. That's how it knows.
Yeah. For raster specifically, you have to tell it that it's a zar file.
You have to tell it that it's zar, because it doesn't know that string. The rasters detect it. So you just say source is zar source.
Right, and then ultimately zar gets the string from.
Yes, zar gets the string.
Interprets that.
Yeah, based on this reference : / zar will know to interpret whatever it sees as a Kerchunk file. If you've loaded Kerchunk. If you haven't, then all bets are off.
So just saying the implication is that at some level for Kerchunk or zar, there is a list of known formats.
Yes. But I think that's the case for most file I/O libraries these days.
Yeah, that's
Yeah.
fair. I was wondering what.
Yeah. So, right, so this was the file format. Now, one disadvantage of Kerchunk is that it's completely flat, right? So if I look at this file, this is fine when it's just 3 or 4 files. It's fine when it's 100 files or 1,000 files. When you get to the point where you have 1 million chunks, 2 billion chunks, 1 billion chunks, then you run into problems. Because you have to parse through this entire text file or look through this entire dictionary every single time you want to retrieve a chunk. And there's some ways to accelerate that, but fundamentally, the problem's still kind of the same. So nowadays, there are a couple of new technologies that have come up. So virtualizar is one of them. It's basically just a way to. Virtualizar started as a way to create these chunk manifests in software, right? So what you would do is in Xarray, or if you use dimensional data in Julia, right? And dimensional data is our equivalent. Every data set, once you get down to the bottom level, there's some array which backs that data set. There's some matrix in memory or 3-dimensional, 4-dimensional array in memory. And what virtualizar did was it said, okay, instead of faking out the file system, let's fake the array representation. And the array is what they call a manifest array. And it's changed a bit since then, but I just want to explain sort of how this came about. The array is what they call a manifest array. And when you requested a datum from some index, or when you requested a certain chunk, that manifest array knew where that chunk was located. It went, it located it, it downloaded the data, decompressed, and returned it to zar. And so this was basically, what you gain with this is a little bit of hierarchical structuring, which this doesn't have, because this is just a list of file names. And now virtualizar is actually built on top of Kerchunk. So all the capabilities that Kerchunk has, virtualizar has as well. It can emit Kerchunk files and things like that. So let me now open the web. And so virtualizar is a GitHub repo, right? If I zoom in a bit, is this readable? Or should I zoom in a bit more? Sweet. So yeah, well, the other thing about Kachunk that I forgot to mention is by nature it's completely cloud optimized, right? Because every potential bit of metadata you could want is in this JSON file, which you just download. So you don't have to refer to the cloud at all unless you're retrieving data. So yeah, virtualizer kind of grew out of Kachunk. This manifest arrays thing is kind of an intermediate layer in memory. And if I look at, this is in Python, of course, but given that you can always call Python from Julia by Python call, this is usable as is pretty much. So the way you do this right now is you would use this concept of a virtual data set, which, let me zoom in a bit more. So you would open these virtual data sets, you have all of this bunch of files that you want to make into one data set. So you'd open them with virtualizer, you'd use Xarray to combine them, and then you would dump that out as a Kachunk file. And then you can just use Xarray or kachunk.jl and zar.jl to open this as a zar array, essentially.
Have you thought about adding this to kachunk.jl? Because rasters can already do that combining.
Oh,
So we can easily just write that.
so now we didn't have concat disk arrays before.
Yeah.
Now that we do, one thing we can do is we can create a virtualizer like manifest array in Julia, and then, yeah, life becomes a lot simpler.
Like you can just open the folder as a raster series, and then you just combine the raster series and be a concat disk array.
Yeah. Well, the big thing, so another
With all
one.
that code at the top, you just can't say that it's a kachunk.
Yeah. One of the big things that Kachunk did, right, is it actually, a lot of the hard work was figuring out how to get the byte ranges out of these files. And so if that is solved, then there's no reason you couldn't have a Kachunk in Julia. On the flip side, I mean, would you really want a Kachunk in Julia? If it already exists in Python, it seems like it may be useful, but it seems like a lot of effort that could be spent elsewhere right now. So to my perspective, a reader is probably fine. Most people who are Kachunking their data sets will do it in Python anyway. I mean, the potential to convert them to Julia is quite low.
I think the generation of Kachunk is very much provider specific.
Yes.
As opposed to user specific.
Yes. Because, well, I mean, the thing is, right, generally, if you have a 1.4 petabyte data set, it's very, very difficult for me as a user to create a Kachunk of that. But it's very easy for the person who's generating that data set. As you generate it, you just spit out a Kachunk file too. Right? That costs you nothing. So,
Maybe another comment to this.
Mhm.
I think it's very useful to have a package called kachunk.jl, because the same way, the first question I get whenever I try to tell people that we use Python, look at Julia, they ask me, where is my survey? The next question that comes up is sometimes, where is my kachunk? And being able to rightly point to that,
yes.
opposed to something like some data, is quite useful if I know.
Yeah.
Which you can do.
No, absolutely. Let me actually. So we do have a kachunk.jl. What happened here? Oh no. Okay, I have to look at that. But yeah, we do have a kachunk.jl. You can just install it. It kind of works out of the box these days. Yeah, I need to update the documentation, but it does exist. And for most kachunks, it'll work okay. There's an ignored part of the Kachunk standard that they defined, which is basically like generative templates. So you could define a list of variables that Kachunk would for loop through and do nested loops and kind of try and generate byte ranges. The problem with that is, of course, that byte ranges are arbitrary, effectively. So there's no way to encode that in a more compact way than listing them all out. So but some files still use that, but that's not really a big thing, I think. There is another package called fspec.jl. Oh, 5 minutes. Oh, I only have 5 minutes. Okay. Let me run through this really quick. So the new hotness is called IceChunk. And this thing is basically building on top of virtualizer and Kerchunk. And the idea is that what would happen if instead of storing my ZAR chunks in these directories and nested folders and whatnot, I just store them as content address binary blobs, right? Some random hash as a binary blob. And then I have a metadata file that given a chunk address points to that binary blob. The advantage of this is twofold. One, if you have a Kachunk dataset, you can't write to it, ever. Because the moment you write to it and change the length of that chunk, you've broken the entire Kachunk file. Because you've broken the bit ranges, right? They're no longer the same. So with IceChunk, what you can do is, IceChunk supports either you have a single file, which is a chunk, you have multiple chunks in one file, or your chunk is just file, byte, and byte range. And so what you can do is you can start with a Kachunk file, and then as you edit this, IceChunk will automatically replace what you have with local chunks, effectively. So, but the big thing with IceChunk is not that, right? The big thing is that it's meant to be a transactional storage engine. What does that mean? Because your chunks are not directly stored, they're referenced, your metadata file can just be a single, you can use like a Git style interface for your metadata file. And so whenever you change a chunk, that's just a change to the metadata file and a new file in the chunks somewhere. But if you store the metadata file before and after you made the change, you can roll back that change back. And that means that you can coordinate changes coming from multiple users or from multiple jobs on your distributed task or whatever, right? Because earlier what used to happen, if you changed the ZAR chunk, you would change the entire chunk and you would have to upload that chunk again, which is still the case here, but the chunk would go to x/1.2.3. And if another user is trying to write to x/1.2.3, you don't know which one worked. So your data is now effectively corrupted, or at least wrong. And with this, one transaction will fail, the other transaction will succeed. And you know which transaction failed. So then you can redo the computation or whatever you have to. And IceChunk actually, they also implemented their own I/O in Rust, so it's, I think, a factor of 2 faster than what they have in Python right now. So that is also an advantage. But the file structure is again a bit more opaque because you have this metadata file and then you have all of these like random content address chunks. So I think it's definitely something that people should look at, but it's a trade-off as to what you need and why you're using it. So yeah, I guess my time's probably up.
I have 1 minute.
1 minute, okay. Any really quick questions? All right.
Actually, there are some subtle difference between NetCSCS and ZAR.
Mm-hmm.
For instance, when you have the fill value.
Ah, yes.
So in NetCSCS it means it is missing, while in ZAR it rather means it's a default value. Yeah, like if you
Yes.
have a parser with
Yeah.
the default value would be 0, but it doesn't mean
Yeah.
it's missing, it's just 0.
Yeah.
And the thing, another thing is that you cannot store none in the as a number. As a JSON file, you have to store it as a string.
Mm-hmm.
So you cannot have an attribute which has the value none except for the fill value.
Except for the fill value, yes.
Which is as a special.
Yes.
So did you come across?
So I came across a couple of CF issues, but not that specific one. That being said, yeah, because the CF implementation is so different. Felix, you're saying?
Regarding the difference between fill and missing, there's in ZAR generally there's also fill as missing keyword argument and force it to use to replace the fill value as missing value. Because sometimes you want to have that, and sometimes you don't.
Would be better if I have a different name. So that's would not
It's,
That's a distinction in the self-specification.
yeah.
Use case. Because basically, in ZAR, if your whole chunk is only is not there, it will fill it up by default. That's the point of the code. So that you don't have to write the chunks that are not there even as empty files. And then you can use that as a missing argument to say this is actually missing argument later, or you can use it as
Right.
Something related to this is also the chunks are not there. Some servers report permission for missing chunks. And
That's a problem.
unfortunately, that's how many servers are configured, and it's not going to change. So even if you have if something's not there,
Right.
you get an error like permission added.
That's awkward. I mean, I imagine that that's probably something that one could look at in zar.jl itself in the way that it handles HTTP replies, right?
Yeah,
But
Citrix already implemented a special case.
Okay.
Where you can say, okay, if it's permission denied, I will just
Yeah. Just assume it's missing.
It's not there, but not the default. So
Oh, sure.
Just a different question. Maybe you could now maybe data in the notebook. Do you have examples of actually working with chunk data or ice chunk ideas in Julia?
Yeah, so ice chunk, not yet. It seems doable to do like an interface through Python to Julia for ice chunk, but still have to figure that out. In terms of chunk, there are a couple of examples that I have, but the problem is that the data sets keep getting updated, so the files that I have keep breaking.
Yeah, it does seem to be in flux.
Yeah, it's a bit tough, but definitely doable. I can shoot over some notebooks and stuff like that.
So is that a problem for Python as well?
Yes, any consumer of chunk will have the same problem if the data set changes.
You actually keep getting
Yeah.
chunk files.
Yeah. Well, I mean, you can refer to a chunk file on the web, so you don't necessarily, but you have to download it all the time. But that's not so bad. But yeah, I mean, in terms of minimizing complication, I think ice chunk is the way forward, in that sense, because it's storing everything controlled by the provider, right? So, yeah, cool. Well, I think Martin, you're up. Thank you.